I wanted to revisit the idea of common ions and solubility. When you have a solid in a solution that has a common ion with that solid, what's going to happen is the solubility of the solid will drop. Le Chatelier's principles say that if a concentration of a reactant or product were added to that chemical reaction, and the reaction would shift away from the increase. So in this case here, if we're looking at magnesium hydroxide, and we're going to add it to a base. So we want a base that's going to be a strong base, something that's going to disassociate, that has hydroxide ions in it, so that we have that common ion. So if we were to put magnesium hydroxide in a solution of, say, potassium hydroxide, that potassium hydroxide is going to have OHs. And so once you have that common ion, it's going to cause a shift so that less of the magnesium hydroxide would disassociate. So having a common ion is going to lower the solubility of a solid. Okay, so let's calculate what happens when we have a solid calcium fluoride in a solution of sodium fluoride. So in this case, this here is a solution. The sodium fluoride is a solution, so that's going to disassociate, and what's going to happen is it's going to contribute, and we're going to have a lot of fluoride ions floating around in solution. So what we want to do first is we want to set up our reaction for the dissolution of sodium fluoride, not sodium fluoride, sorry, calcium fluoride. So we have solid calcium fluoride, and when it disassociates, it's going to go to that equilibrium. We're going to get calcium 2 plus 2 fluorides. So if we were going to just set up the KSP, KSP is going to equal the concentration of the calcium times the fluoride, and we're going to take that to the second power. So what we're going to do is we're going to try and see, we're going to try and solve for the molar solubility. So when we're ever solving for the molar solubility, we're looking to solve for X. Okay, so we can do that right here because we know that as calcium fluoride disassociates, calcium will be X, and the fluoride will be 2X. Now, what we're given is that we're given the molarity of the fluoride ions in solution, because this molarity is in solution, and it's going to be so much higher than the concentration or the F negative in solution from the calcium, that we can say that all of the fluoride ions is going to be coming from the sodium fluoride. So right here is going to equal 0.025. And again, I'm getting that. I'm just getting this from right there. Okay, so let's set up the KSP. Well, the KSP is 4.0 times 10 to the negative 11. And we want to solve for X, so I'm going to turn this into X values. Or not, we'll just keep it this way. Right here I'm just substituting for F, but don't forget we need to square that. So if I were to calculate this out, the calcium ion, or X, is going to equal to 4.6 times 10 to the negative 8 molarity. So there's your molar solubility right here. X equals the molar solubility. you were thinking, why? That's the concentration of calcium. Well, remember, this is X, and that's F is 2X. So we're just solving for X. So what I'm going to do in the next slide is show you what the molar solubility would be if we had the solid CaF in water. Okay, so the molar solubility of CaF in a 0.025 molar sodium fluoride solution was 6.4 times 10 to the negative 8. So let's see what would happen if we had that the calcium fluoride in just water. So we would still do dissociation, CaF2, break down to form Ca2 plus 2F minus. There's my X, this is 2X, my KSP, and we're going to use the same KSP as what we used previously, equals the concentration of Ca2 plus times the concentration of X, I'm sorry, not X, of F negative, and then we're going to square that because of the coefficient. Okay, so we're going to, now I'm just going to substitute my numbers into here to solve for X. So from the previous question, the KSP is 4.0 times 10 to the negative 11 equals, now calcium is going to be X, and this is 2X, and we got to square that. So 4.0 times 10 to the negative 11 equals 2x squared is 4x squared times x. So it's x times 4x squared, which is all equal to 4x cubed. So I'm going to just erase it just to make it neater. We got 4x cubed. Now to solve for x, I'm going to divide both sides by 4 and then take the cube root. And so my x value is going to equal 2.15 times 10 to the negative 4 molar. So if you can compare the two, you could see that this value here is larger than this value here. So what's happening is this shows us that there's less ions in solution when we have a common ion. So smaller number, smaller ions in solution. Well, I shouldn't say smaller ions, less ions. Less ions in solution means that it is less soluble. Q is the reaction quotient. We're going to use this to determine if a precipitate will form. And we could also use it to find out the concentrations of the ions, what concentration of the ions are needed for a precipitate to occur. And I know this is it. The program kind of overlapped over itself. It should say Q, the reaction quotient, is used to determine if a precipitate will occur and what concentrations of an ion are required for a precipitate to occur of an insoluble salt. So that insoluble salt is kind of overlapping over the second part of the PowerPoint. So if the KSP is greater than Q, then the system is not at equilibrium. The solution is unsaturated. So in order to get to equilibrium, we need the reaction to run to the right. If the KSP equals Q, then the system is at equilibrium and the solution is saturated. If the KSP is smaller than Q, then the system's again not at equilibrium, but this time the solution is supersaturated, so if we want it to get the system at equilibrium, we need it to go left and we need it to go back to the solid state. Okay, so here's a question. 50 mils of a 3.00 times 10 to the negative 3 molar FeSO4 solution, should be 4. FeSO4 solution is mixed with 50 mils of a 4.0 times 10 to the negative 6 sodium hydroxide solution. Does a precipitate of the iron Roman numeral 2 of iron hydroxide form? The KSP is 1.6 times 10 to the negative 14, and that's the KSP for iron hydroxide, or iron Roman number 2 hydroxide. So first things first, if we want to find out if a precipitate is formed, what we have to do is we have to calculate QSP and then compare that with the KSP that's given. So we need molarity, and we also need to realize that since we're mixing solutions, we need a total volume. So my total volume is 50 milliliters. I'm sorry, my total volume, total after I've mixed it, is 100 milliliters. So what I want to do first is I want to calculate the number of moles of iron 2 sulfate, and then calculate the number of moles of the hydroxide and sodium hydroxide, and then use those moles to calculate molarity. Alright, so let's get started. So this is what I'm going to do. And I'm going to keep these in millimoles since I have milliliters. So mole equals molarity times the liters. So I have my molarity is 3.0 times 10 to the negative 3 times 50 milliliters. And I know I'm not keeping my significant figures in here. I'll put them back later. It's going to equal 0.15 millimoles, and this is of my Fe2 plus ion. Only a little space. Okay, and then I'm going to do the same thing for the moles of hydroxide ions. So I have the molarity of that is 4.0 times 10 to the negative 6 this time. And I'm going to multiply that by my volume, 50 milliliters, and that's going to give me 2.0 times 10 to the negative 4 millimoles of OH. Okay, but when I'm calculating QSP or I'm calculating the KSP, I want molarity. So what I have to do is I have to take my total moles, my total volume, and my total volume, if we can go back and we look, it's 50 plus the 50 because it's two solutions to be mixed together. So to calculate molarity, remember molarity equals moles over liters. Moles over liters. So since I have moles right here, I'm just going to divide it over milliliters this time. I'm going to keep that milliliter in here, then I can cancel out milli and milli. Okay, I'm going to do the same thing over here. Divide that by 100 milliliters, cancel milli out. Okay, so this gives me 1.50 times 10 to the negative 3. And this is going to equal, give myself some more room, 2.0 times 10 to the negative, negative 6. Yep. Okay, so now I can use my two molarities here, this molarity and this molarity. Now I can use that to calculate QSP. So QSP, and we calculate QSP basically the same way as we calculated KSP. So it's the concentration of the Fe2 plus times the concentration of my OH negative, and since there's two OHs, I got to square it. So my QSP equals 1 point, oh, that looks messy. Looks like a 7. 1.5 times 10 to the negative 3 times 2.0 times 10 to the negative 6 squared. So QSP equals 6.0 times 10 to the negative 15. So now we have our QSP value right here. And what we're going to do is we're going to compare that to the KSP. So, which one is bigger? QSP, KSP. So the KSP is greater than the QSP. So therefore, I'll just write it out. So then the reaction is going to run towards dissolution. So precipitate will not form. Okay, so we're going to do the same thing. We are going to try to determine whether precipitate will form. We have two solutions, and we're going to mix these two solutions together. So things that I want to think about is my total volume. So I have 750 mils of one solution, 300 mils of another solution. So we have a solution is prepared by adding 750 mils of a 4.00 times 10 to the negative 3. I know it's hard to see, but that says negative 3. Molar cerium nitrate to 300 moles of 2.0 times 10 to the negative 2 molar KClO3. Will cerium iodate with a KSP of 1.9 times 10 to the negative 10 precipitate from the solution? So let's just write a couple things down. I'm going to need my total volume because we're mixing solutions. So total volume is going to equal 1,050 milliliters. I know I need to calculate QSP because I need to compare QSP with KSP to see if we will have a solid or precipitate that forms. So let's do the dissolution reaction for cerium iodate, and then we can find the QSP equilibrium reaction. And then we have to calculate the molarity of the cerium and the iodate in solution. Lots of steps. So here goes. Here's my reaction. Cerium iodate, IO3, 3. It's going to break down to form Ce3 plus 3IO3 negative. So this is X, this is 3X. But now when we do our equilibrium or our QSP expression, QSP is going to equal the concentration of Ce3 plus times the iodate, but we got to cube this one because we have a power of 3. Okay, so there's my equilibrium expression. Now let's convert to, let's find the molarity of these two things, of the iodate and the cerium. So for the Ce3+, I have 750 milliliters times the concentration. It's 4.0 times 10 to the negative 3. And so that's going to give me 30 millimoles of Ce3+. And for my iodate, I have 300 milliliters times a 2.0 times 10 to the negative 3 molarity. So I get 6 millimoles of iodate. Now let's convert this to molarity. So molarity is going to equal 30 millimoles divided by the total volume. I'm going to do the same thing here. 6 millimoles divided by the total volume. Okay, so I just calculated out what would happen if I took 30 divided by 1,550, and so I got this number right here, 0.00286. So that's my molarity of my cerium. I did the same thing here, and I calculated my molarity of the iodate. So now what I'm going to do is I'm going to take these two numbers and then I'm going to plug it back in. I'm going to plug it into this formula right here to calculate my QSP. Okay, so I just rewrote my molarities of my cerium and of my iodate. So QSP equals, and we wrote this up before, is the concentration of the cerium, concentration times the iodate, and that was cubed because there's 3 iodates to the cerium. So let's just plug in our numbers to solve for QSP. So QSP equals 0.00286 times 0.00571 cubed. So QSP equals 5.3 times 10 to the negative 10. So let's compare our QSP with our given KSP. So if we go back and we look, I think our KSP value was given to us as 1.9 times 10 to the negative 10. So KSP is smaller than QSP, therefore the reaction will run to the left. And if we looked at our original equation, that means that solid will form. So solid can't cross that out. Can't erase it for whatever reason. Solid Ce, solid cerium iodide. Solid cerium iodide will form because the KSP is less than QSP. Last problem. Now this problem has to do with a common ion, and I know you can't see the top line, so I'll read it out to you. It says a solution contains 1.0 times 10 to the negative 4 molar copper 1 ions and it contains this many 2.0 times 10 to the negative third molar lead 2 ions. If a source of iodine is gradually added to the solution, will PbI2 with a KSP of 1.4 times 10 to the negative 8, or copper 1 iodide form first, or which precipitate will form first? Then what is the concentration required to begin the precipitation of each salt? So what we're going to do is, this is like a common ion idea. What we want to do is we want to calculate the concentration of the iodide ion for the lead 2 iodide and for the copper 1 iodide. Whichever molarity is smaller, that's the one that will precipitate out first. Okay, so let's do the lead iodide first. So KSP. Well, let me. KSP equals the concentration of the Pb2 plus times the iodide squared. Since the KSP equals 1.4 times 10 to the negative 8, we want to find, oh, and we already have the concentration for the lead. It was given to us. So that's 2.0 times 10 to the negative 3 times iodide. But we need to square that. So I'm just going to divide both sides. Okay, and that equals I squared. So then we want to take the square root of both sides to just get iodide. And I'm getting 2.65 times 10 to the negative 3. Okay, so that's one of my iodide concentrations. Now, let's do the same thing, but let's do it with copper. So I'm going to change to blue. Can I erase a couple things here? Makes it a little bit smaller. Okay, so I'm in blue now. So the KSP for copper is the concentration of the copper. Oh, so messy. Times iodide, and that's a 1-to-1 ratio. So then I can just write 5.3 times 10 to the negative 12 equals, since we're given the KSP of the copper, I'm going to say equals concentration of I, and divide it by the given copper concentration, which is 1.0 times 10 to the negative 4. So my iodide concentration is equal to 5.3 times 10 to the negative 8. I just have to double check that. Negative 12 minus negative 4 equals negative 8. So, which one's smaller? Which one is smaller? So, well, this one. Since all we need is a concentration of 5.3 times 10 to the negative 8, as soon as we hit this concentration, we'll hit the smaller concentration before the larger one. So that means that CuI will precipitate first. And then to answer the second part of the question, what concentration of I is required to begin the precipitation of each salt? Well, you need 5.3 times 10 to the negative 8 concentration of iodide to start the precipitation of the copper iodide, and then you need 2.65 times 10 to the negative 3 molarity for the iodide to make lead 2 iodide. Okay, so this is that's all I have for solubility, for the KSP of solubility. So hopefully you'll listen to this, because I'd like to do like maybe one practice problem on Monday, and we're going to start in with electrochemistry and finish it up by Tuesday/Wednesday, and then your test on Friday. A couple study sessions, and then the big AP test on Monday. So thank you for listening. I'll see you tomorrow, or maybe I'll see you later on today.